Hello guys and welcome in this new recording. Yes, I know it's been a very long time since I made my last video. Um, Maybe you have started to think I was dead or something, but I'm still here. It's just that I had my father on vacation here, so I was trying not to spend too much time in front of the computer for a change. But anyway, now vacation time is done, and I finally have some time to get back to my Nerveland project. So yes, let's just get started with another quite interesting component here, because I have been working on the atmosphere rendering. So if you remember, in the previous recording, I was working on displaying the terrain, so basically displaying the complete Earth itself. And now I am trying to work on the atmosphere scattering pre-processing. So let's dive into this. In fact, it's another part of the work done by Eric Bruneton, and you also have that in fact on the Roland website. So I was navigating a little bit on that, and yes, the display of the atmosphere on the Earth model here is done with this pre-computed atmospheric scattering algorithm. So this is definitely going to take a few consecutive recordings to cover everything, but for the moment, let's just say I would like to give you kind of overview at least, and yeah, we'll try to go slowly and we'll see how this goes. First thing I think we should start with is this web page. So this is a description of what is the precomputed atmospheric scattering algorithm is supposed to be. And in fact, this is a new implementation of that algorithm, because the initial paper, which is available here, I believe, so publication, we should have Precomputed Atmospheric Scattering. Yeah, it was in 2008. And this new implementation here was done in 2017. I guess mainly because the author wanted to clarify the implementation, provide more detail, provide some documentation. And this is what is done here. So this page is the entry page where you have a basic overview of what this algorithm here, and it's also describing the structure of the file that you have on the corresponding GitHub repository. And well, we're not going to cover everything here, so if you want to go with the details, you need to check this content. But all you really need to know is that the algorithm itself is written with C++ and OpenGL. So all the shaders and stuff, these are in GLSL. And the idea I have again here with the Nerveland project is to port everything into WebGPU soon. So yeah, we'll have some work to do here. Anyway, among those files, this folder here contains mostly different files to provide you a demonstration of how you actually use the pre-compute data. The reference folder here is, I think, the initial implementation itself. And what we really need to pay attention to also are those 5 files here. So the constant, the definition GLSL, function GLSL, and model class. And if you go, for instance, and you click on this one, it's going to give you additional pages with documentation on what the file actually contains. So it's definitely worth reading to try to understand a bit better what's happening here, because documentation system is very clear, very complete. So if you're not familiar with that, you should read this content. Another key element maybe is this one, the function GL cells. This one is a core functions list for everything that you need to do the computation and pre-computation of the atmospheric stuff. So it contains all the details you need to know concerning how you compute transmittance texture, scattering texture, the irradiance texture, and it's also providing you nice diagrams like this one, for instance, trying to explain what is actually happening. So yeah, you want to have a look at this also to understand what you're doing. But I must admit that I didn't spend too long actually reading this myself. I had been working on the previous implementations of the previous paper here. This one I have read and reread multiple times because I was trying to implement that at some point. And it was working, but I was still using GLSL, so it's a bit different now. But yeah, I didn't really spend too long rereading this content again. All you really need to keep in mind in the end is that your model here, let's get back to the model that you have here, is going to pre-compute 3 separated textures. So the transmittance texture, the scattering texture, and the irradiance texture. And with those 3 textures, then you can compute the atmospheric display quite efficiently at runtime. So you need to pre-compute those 3 textures, but everything else is done at runtime. So yeah, but the pre-computation itself is a bit tricky. And yeah, what else? Another thing I wanted to mention is if you go on this page, you should have a mention at some point that, yeah, there's the online demonstration of what this atmospheric display is doing. So this is the page I opened just here. So this one is the WebGL 2 implementation of the algorithm, and it's demonstrating the display with a simple sphere on the surface of the Earth with the sun lighting the scene and with the atmosphere rendered normally properly. So you can move away from this sphere and you can move around, so you get different display depending on your point of view. You can even go into space, still get the Earth surface displayed properly. And you can also move the sun around if you use control, then to control left click with the mouse. Okay, so yes, I guess this is it. You have different point of view also. 1, 2, 3. 1, 2, 3. Okay. And 9. Okay, I reached the last one. Next thing you need to do is, when you got an understanding of all that, is to have a look at the GitHub repository. So that's the GitHub repository for the new implementation. And this is, of course, where I started my journey myself. And so let's now move to what we have here on my local machine. So that atmosphere model is what I have implemented myself. I'm going to give some details on that part. In the atmosphere folder, that's the only thing I really have for now. The constants also, this is basically the same as the constant file that you have. Okay, and the source project I use is this one. So the atmosphere here, then you have demo, reference, and those are the source files. So that's a checkout of the reference GitHub repository. And the idea then was basically to try to replicate this model class. Now, that was a bit tricky, so I'm not quite sure where I should start. First thing you need to notice is to create the model itself, you need quite a few parameters. So that's the constructor. In fact, model constructor here, you have all this list of parameters up to this line. Then you just have a simple destructor, the init function here. You can get access to a shader, set program uniforms to set up a program, okay? And the important function is this one, the precompute function. This one is going to do all the AV work actually, starting from the init, I believe. So if you go into the implementation part, let's just bypass all the shader definition here. So you have, well, these are helper classes and functions that are used to set up everything in GLSL. And on my side, I didn't really need that at all because we're not using GLSL anymore. So I'm not really spending time on this part. Draw quad, yeah, that's how you would draw a quad, but in WebGPU that doesn't work anymore. We have to set up a full pipeline, and also it's a different mechanism. So we'll get to new implementation in a moment. And so a lot of helper function. Then the constructor here. This one is going to set up a lot of stuff. And there's this part which is interesting, which is a custom function which is providing, in fact, some constant element in the shader itself. And this was used then as some kind of header that was included in many different shaders. So the init method itself, that's where you're going to do the initialization of those three textures which I mentioned. And by the way, what I did not mention was that the transmittance texture is a 2D texture, the irradiance texture is also 2D, but the scattering texture is actually a 3D texture. The transmittance is the easiest one to compute because the program used to compute that one is straightforward. But then when it comes to the irradiance and the scattering texture, that's where you really have some tricky details coming in, because both of them depend on the transmittance texture, but they also are computed progressively with different iteration on the texture. So using the previously computed irradiance at a given level, or actually scattering order, and using that as an input to compute the next level and adding that to the final texture. So that's where you have some tricky operation. But in the init function here, you're going to set up a few textures, and then you're going to start calling this precompute method. But you're calling that, I mean, multiple times. So there's one here, for instance, and then for a number of iterations here, you are going to set up some matrices, blah, 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 then call that again. Then you're going to re-render transmittance here, I believe. And everything is really done in the precompute function itself. If I can find that one, you see that you're starting with a few input textures, a vector and a matrix actually, and some additional uniform elements. And you're going to set up a program to compute transmittance, another one to compute the direct irradiance, and the single scattering, then the scattering density, indirect irradiance, and multiple scattering. And so that's when you draw a quad here, that's where you actually compute the transmittance, and then you compute the first step of the irradiance here, I think, direct irradiance, yes. So you draw the quad here. And another thing you need to pay attention to is, for instance, here for transmittance, you just have a single frame buffer, so you're rendering a single texture. But for this one, for instance, you have two attachments. So first one, which is storing the delta irradiance texture, and another one which is storing the irradiance texture itself. So you're rendering two textures at the same time. When you do that, you need to deal with the blending also for each of those textures. So for the first one, for instance, we're not blending anything, but for the second one, you could be blending, which means that when you're rendering into the irradiance texture, if blending is enabled, blending is set up this way. So you're adding the RGB part, you're adding the alpha part, and the coefficient for the source and destination are always set to 1. So it means you're actually accumulating your new input into what is already set into the irradiance texture in that case. So using the blending mechanism on the GPU, which actually led me to another issue, but we'll get back to that one. Anyway, that you have this pre-compute function set up. It's going to do a few different drawing of quads to render to the target texture every time. So you have transmittance texture, scattering, and irradiance. And also, as I said, as you see here, for instance, you have a for loop where you have some operation done one after another inside a for loop. So that's where you have the most tricky part of the computation, in fact. When you're done with that, normally you basically have all your required atmospheric texture pre-computed. Yippee! Okay, that's basically where I am myself in my implementation. I went just a little bit further because, as you see, I have a few changes here, and those changes are to then start using those the result of those pre-computed textures. So the result of the pre-computation stage, in fact. But this is still work in progress, and yeah, I have not completed that yet. So what we need to focus on maybe is yeah, what we have done to do the pre-computation themselves. So first thing is this: for the construction of the atmosphere model, if you remember, there were a lot of parameters for the constructor. So I decided to encapsulate all those parameters into a structure which is called threads. And you're just providing a single of those threads to construct the model. Another thing I have provided also is a static function here to prepare the threads corresponding to the Earth atmosphere. You have that, I believe, in the demo part. If you go into demo, when it comes to setting up a model to do some kind of rendering here, you are going to set up a model with some of those parameters to simulate the Earth atmosphere. So all of those elements are the proper settings for the Earth. So yep, I have taken all that, and that's what you're doing with these get Earth threads. And then you return a big structure containing everything like that. All right, next. So when you get the threads to construct the atmosphere model like that, you have a few computation done in the constructor of the model. Except that in that constructor, Mr. Bruneton was using a lambda function to, well, generate some. I mean, you're providing a function which is going to generate the heater when you need that. Yeah, I could just as well not store all those values, I guess. Not quite sure, but I went on a bit of a different path because I'm just storing everything, I believe, here in the class itself. It doesn't really hurt anyway. You just have a couple of vectors, that's all. And then you start with preparing your textures. So that's where I'm starting to use my GPU engine myself to generate the textures. So you have this one which is 2D, scattering is free, as I mentioned. In irradiance itself is 2D. You may have another one here which is the optional single scattering texture. Then yeah, this is basically the function I use to produce this header, which is similar to that function here. And another, yeah, then you reach the init function at some point because that's how you're going to do all the pre-computations. So this one is kind of similar to what we have in the base model. So this one was the init. So it's doing the same thing, but again, we translated everything into WebGPU to create the required temporary textures in this case. And then you start calling the precompute function. This part, yeah, is similar to what we had in the model CC file. And yep, this one is still missing. I need to recompute the transmittance at the end. And finally, yes, you see that we are reaching the precompute function itself. And that's where the funny stuff is going. Another key change that I made when coding this code was to use directly compute shaders instead of Vertex and Fragment shaders. Why that? Because I think it's cool. And also, it's simplifying a bit my life, because when in the reference implementation, transmittance, for instance, is rather simple. Okay, direct irradiance, you render into two outputs. So this already, I guess, yes, it's possible to do that with GPU. It's just that my engine itself is not really ready for that. Maybe it would not be that tricky to add support for multiple targets, but it's something that I have not tried. Whereas if you are using a compute shader, you can basically set up texture storage as part of your binding group, and you are going to write whatever you want into this texture storage, and you're not limited to a single texture storage, so you can have a couple of them, or even 3, 4 if you want. I think you can have 3, 4. And yes, you could be writing to multiple textures at the same time from the compute shader. And also, generally speaking, since we're doing precomputation here and we want to generate, well, mathematical results that are not really related to anything you want to display, it makes more sense to be using a compute shader anyway, rather than a fragment shader to do the actual writing into the texture. So this was a big reason. Another big reason for me was that the implementation, where do we have this? Geometry shader. Yes, geometry shader. Okay, I found it. For instance, here, when you do the compute signal scattering, you're going to use this geometry shader, and this one is here. So you want to basically render to different layer, 3D textures in this case. Except that if you are rendering with a fragment shader, you can only render into a slice of this 3D texture. Whereas if you are rendering with a compute shader, in fact, you can attach the full 3D texture as a texture storage, as a 3D texture storage, and then you can write anywhere. So you could be writing all the layers of your texture with a single compute shader. And in fact, this is what I'm doing now. Whenever there is also this concept of layer, you see that here you would normally be iterating all the layers that you have in the 3D texture for scattering. You would change the binding for the layer value. That would state the behavior of the geometry shader, and would then make you target a different layer of the 3D attachment. But we don't need that on our side, because we just iterate on the layers directly in the shaders. So which shader was that? This is for the compute signal scattering. Let's have a look at the shader files now. So when it comes to the computation here, as you can see, we have a compute shader. If we are out of the bounds, we don't do anything, and otherwise you're going to iterate on the layers just here. So you're going to write to your target textures, which is 3D, taking into account the appropriate layer. Okay, yeah, when you use the codes here, you compute things differently, and you get some value. Okay, all right. So this was another big difference, I guess, compared to the original implementation. And then Yeah, basically, I just spent a lot of time trying to get this to work properly. I went very slowly and progressively in the pre-compute function here. And at first, you just start with setting up a single computation step if you want, the computation program here to do the transmittance precomputation. And I just added additional step progressively when each of those steps was working fine. So yeah, I built the complete function here for precomputation, just starting from the beginning and doing it step by step. The way I was able to figure out that it was working was to set up a unit test, in fact. So I have a unit test for this atmosphere model. So this one is going to create a simple atmosphere model. Then when you have that model, you're just going to call init, and it's supposed to initialize the textures in that case. And then you just wait until the engine is done. And normally when you reach this point, you know that there was no error and the computation went fine. I still need to be checking the content of the texture themselves to try to find a way to ensure that the computation is correct and the content that I have in the texture is indeed what it's supposed to be. So this will be done somewhere here, I guess. So I will download the textures, starting again with the transmittance only, and then try to replicate the computation that was done on the GPU on the CPU side and compare some of the texture pixels to see if I have the same values as what was computed on the GPU. So this is still to be done, and that will be probably for another recording. What I can do already is just try to run this unit test to give you an idea of how long it takes to do the pre-computation, and we're done. So yeah, it takes a few seconds already because there are quite a few for loops with a good number of iteration doing integration and everything, and you do that multiple times for multiple scattering audio and so on. So it takes a noticeable time in the end, but it's not very large either, so that's pretty cool. Which means that technically you don't really need to store the result of the pre-computation, still maybe depending on the GPU that you have, because here it's 3080, yes, a pretty good GPU already. Maybe it would be worth storing those files anyway, we'll see. I guess this is it for the overview. There are probably additional stuff I should mention in the initial implementation. To construct those shader here, you see you would normally use some basic shader like this one, compute transmittance shader, and you would concatenate on top of that the header part. So the header is result that you get when you call that factory function we mentioned, which is provided in the constructor. I could do that also on my side, but as you may know, I have a different system because I can normally just read those shader from file, and so I have a file corresponding to transmittance, and would be inconvenient for me to read the content of this file and prepend some header to it. So what I decided to do instead was to make use of my preprocessor definition system, and for instance this preprocessor entry here, this is what is going to be replaced by the header content, and this is done with this definition that I have just here. So I define the atmosphere definition saying that this preprocessor should be replaced by the header itself. The header would be replaced here. Then this is added as definition to all the commands definition, and those definitions are added to the compute nodes. Actually, they are added to all the nodes that are used here. So yeah, not exactly the same thing as the reference implementation once more. What else should I mention? Oh yes, in the initial implementation, they were using this fragment shader rendering process. So you use in that case the blending stage to accumulate some data in the target texture. So in the case of the irradiance, so yes, you're rendering two texture, and you're going to use this blending function in case blend is activated for the second texture to accumulate the newly computed irradiance value with the previously computed irradiance value. Point is, when you use the compute shader in WebGPU, that doesn't quite work. So the thing is, you can provide those texture storage 2D or 3D into your WebGPU WGSO shaders. And when you do that, you need to specify what is the format for the content you're going to write, and also use this flag, which could be write. And now you can also specify, in fact, either read or also read write. But the thing is, to specify read or read write, you need a custom extension to be enabled on your down engine. And this extension is this one, this Chromium Experimental Read Write Storage Texture. And where do I have that? Yes, that's where I would actually create my device, WebGPU device, and I would provide a list of required features. So you would need to activate this feature to be able then to enable this extension here, and to be able after that to use read write here. But to use this this required feature already, thing is, first, it's a kind of experimental feature, so I thought maybe it was not a so good idea to rely on this. And even on top of that, to just be able to activate this feature here, you also need to provide a specific toggle. So you need to provide a toggle stating enable unsafe API. So with this name, this is the kind of thing I usually try to avoid. So not try to enable unsafe APIs. So at that point I decided maybe I should just not go this route for the moment. Just maybe, where do I have this unsafe API? Let me try to find that. Okay, so you have actually the allow unsafe API toggle defined here in the internals down native toggles. You could provide access to this, but I'm not quite sure actually. Are you going to provide the toggles in the construction process for the WebGPU device? So that's another reason why I decided to not push it any further than that. So the end result with this is basically I cannot use this read-write flag for the moment when I'm using texture storage. So it means, for instance, when I need to update the irradiance texture, which means when I need to accumulate a new value with the previously computed value, I can't use a single texture to do that. And what I need to do is to also provide what is the current value from another regular texture, which is what I call here the previous irradiance texture, which is a simple texture 2D. So that's where you're going to read the current value from, and you're going to add your newly computed value to this previous value. So if you go back, down in the shader, you'll see that I'm reading that, I'm adding the newly computed value, and then I'm storing the result in the actual irradiance texture. Point is, how do you get this previous texture then? Because of that, I had to introduce additional steps in my computation. So what I have, for instance, this part is only happening in the for loop where you have all the orders all the scattering orders, I mean, you have in this part multiple consecutive operation to do. So you have this first one, and each operation is using a different shader, so it's using a different compute node. So you're doing this first compute step, then this one, and this one typically is the one I had to introduce myself, which is a copy operation between the newly computed irradiance texture towards the what I call the previous irradiance texture, so I could update the content of this previous texture. Actually, when using WebGPU, you could also perform a different operation on your comments buffer, because you could ask for a copy of one texture to another. The point is, if you do that, you need to perform this operation as a copy, and then you need to execute another compute pass. Whereas what I'm doing here, I have this computation step as a regular computation step in a compute pass. So I can put everything into a single compute pass. And this is what I'm doing here. I have a single compute pass. I'm adding those computation steps, all of them, and eventually you just need to execute this once. So you execute one compute pass. Otherwise, here you would have the first compute pass doing some of the operation. Then you need to record a copy of a texture, then another render pass, compute pass, sorry, to continue with the needed operation, then another copy of another texture, and so on. So that would, I guess, cut a bit the efficiency of all your computation. Or maybe not, maybe it's not making any difference. I just thought it was nice to do it this way. And yeah, that's it. Basically, I'm doing also another copy like this one for scattering, because we also need to accumulate this one. And it means you have those node with no number, then node 1, 2, 3, 4, and you just register all of them here, one after another in a single compute pass. Okay, next time I'm going to, as I said, provide some additional unit tests to check that the computation done for those textures is correct, and also at the same time I need to prepare the actual usage of those textures to start rendering an atmosphere layer on top of the Earth display that we already have. And yeah, we'll see how this goes, but as usual, I'm probably going to have to fix a lot of stuff, so we'll see if we need to come back to anything that I mentioned here already or not. We'll see, maybe we'll be lucky. Anyway, thanks for watching. If you have any specific question or anything, just let me know in the comments as usual, and otherwise see you next time. Bye bye.